Okay, so let's get started. As you all know, there's an exam this Thursday. It's an evening exam in this room at 7 o'clock. Okay. So I'm going to do an exam review very quick just to review the topics that will be covered and roughly what you need to know and the strategy to review the material for the test. I put up a sample exam and solutions on Moodle. Anybody take a look at it yet? Okay. So that's an exam from a few years ago, a real exam. It should give you some sense of what to expect on the test. Look at that. So I'm going to start with the review, but let me first start with how you should go about reviewing material for the test. So first things, we are going to cover material from lectures 1 through 8. Okay, that is everything until semaphores. Okay, that's what we covered in the first 8 lectures. That's what's going to be on the test. My suggestion is that you not open your textbook and start reading the corresponding chapters, because there is material in the book that we have not covered in class. Okay? I'm only going to have questions on things we have covered here. Whatever we did not do is not something you need to know for the test. Okay? It's good to know more things that we cover here in general, but not necessary for the test. Okay? So the right way to go about reviewing material is you start with the lecture slides. Okay? So whatever we have covered on the lecture slides is fair game for the test. Okay? So that's the way to keep this sort of review. So start with the lecture slides and then go to the corresponding sections in the book and read that if you have to get a better understanding of whatever was covered. But I think the way to go about this is to start with the lectures and then use the book to expand, not expand, but understand the lecture materials better. Okay. So anything we did not cover is not on the test. As far as test questions are concerned, you will see a mix. Okay, a mix of questions which involve explaining what this concept means, and then you just need to know what it means and write down what it means. And then the other kinds of questions that will make you work through small problems. We have done several examples of being CPU scheduling. Here is a set of tasks. This is the scheduler. Work through the example and say, indicate when each task is going to complete. Okay? Those are kinds of questions that require you to work through things. And then there may be some design questions that say, if you have this synchronization problem, how would you use, let's say, locks to implement it, or something that will require you to write some pseudocode and design a solution. Okay? So some questions that just test your knowledge of a concept, some questions that require you to work through some problems, small problems, and some questions that require you to design a solution that's based on whatever the question is asking you. And that's roughly what you will see in the sample exam also. Okay, so keep that in mind. That is not going to be all define X, define Y, and just write down 25 terms and the test is over. That's not what the test is about. You'll have a mix of questions. There will be some problem solving and some testing of your knowledge of the concepts we have covered. Any questions on this? Okay, so I'm just going to do a quick recap of the material. We'll start with lecture 1 and go through lecture 8. So the very first lecture, if you remember, was more of a definition of what is an operating system, and it was more of a history lesson of how operating systems have evolved from their early days in uniprogramming to multiprogramming. So you should know all of these concepts. What is a uniprogramming system? What's a multiprogramming system? What's a multiprocessor system? And so on. And one concept we learned there was this notion of Moore's law, which is a law or an observation that describes how technology has improved. Okay? And it says roughly every 18 months to 2 years, you can pack twice as many transistors on a chip. What that means is your machines get twice as fast, or you can get twice as many cores, or you get twice as much RAM. Okay? So doubling in technology, speeds, technology, sizes, and whatnot every 1.5 to 2 years is what Moore's law has basically observed, and that's what it means, and that's how technology is improved. So that's almost an exponential increase in the capabilities of hardware. That's basically helped us do very major or significant gains in what today's technology can do. Okay, so that's what we learned in lecture 1. Okay. Feel free to ask questions at any point in time. Okay. Lecture 2 was a recap of architecture and hardware concepts. Okay. So we looked at I had this picture of what's inside a machine. Okay. We said there's 4 components. There's RAM, okay, there's the main memory, there's the CPU, central processing unit that does all the computation. There are I/O devices of various sorts, and there's a system bus that connects them all. Okay. So you need to keep that in mind as the main components of any computing system. Okay. And then we looked at many different hardware features. Okay. We looked at traps, we looked at vectors, timer instructions, atomic instructions, and we said many of these features were put in place to aid the operating system, to help the operating system achieve its goals. So you need to understand at a high level what these concepts are. Okay, what is a trap, what's a trap vector, what's an interrupt, and so on. Okay. So we looked at those hardware features. So you need to go back and review that material and make sure you understand all of those hardware features. That lecture we also looked at this concept of a system call. Okay. We said basically you cannot trust applications or user applications to perform privileged operations. We said I/O is an example of a privileged operation. Executing the halt instruction on the machine is a privileged operation. You can't let an application go willy-nilly and start shutting down machines. Okay? So you rather trust the operating system to do it, and the way an application can invoke these functions is to make a system call that asks the OS to perform this function on its behalf. Okay? So the system call is an API that the OS exports to applications, but it's also a way for applications to ask the OS to do privileged operations. Okay? Because the OS is trusted. Applications cannot be trusted. They may have bugs, they may be malicious. You cannot trust that they will always do the right thing. So you ask the OS, the application requests the OS through the system call interface to execute this privileged operation. Okay, and we looked at how a system call is actually executed. You execute a trap, you then go into the trap vector that points to the implementation of the system call in the kernel. The kernel is then going to execute the system call. And you should realize that when you executed the trap, you have to save the state of the process and so on. Okay, then the kernel starts executing. So execute the system call, you return the values, whatever the request. Okay? So you need to understand this notion of a system call. Okay? And then in that second or third lecture, we also looked at various organizations for an OS kernel. In particular, there are 4. Okay? We said most kernels started as monolithic entities. What monolithic kernel means is all of the code, but the kernel is one large executable. Okay, they're all functions. Okay, functions call one another. Okay, all the components are executed as one monolithic piece of software. Okay? From an efficiency standpoint, this is good because any component of the kernel can invoke functions of any other component via function calls, which are efficient. Okay? But from a software engineering, management, debugging perspective, monolithic kernels are a nightmare because very large piece of code, you make a small modification in one piece, it causes some ripple effect somewhere else and you introduce some unintended bugs. So you need to understand the whole thing to make small changes. Okay? So that's not a good way to design large software systems. Okay? So, next question.
You said again about monolithic.
What's the question?
You said again about monolithic.
Again about monolithic. Okay. So monolithic kernel simply means that the entire piece of entire kernel is implemented as one large piece of software without any functional division of component. Okay, so everything is implemented as methods or functions that call one another. Okay, that's what is called monolithic kernel. Okay, so in contrast to monolithic architecture, we saw 3 other architectures that try to address this issue of better management and better modularity. Okay, so the layered approach essentially is a way to write any software system in layers. Okay, each component is called a layer. And in a layered approach, you are restricted. Each layer is restricted to only invoking the functions of the layer above and the layer below it. Okay? So layer I can only invoke the interface of layer I minus 1, and layer I plus 1. And that's basically a way to make your system modular. Each module is a layer, a component is a layer, and layers talk to the layer above and the layer below. So we said that's one way to make the system more modular, but it is somewhat restricted because each component can only talk to at most two other components of the kernel, which is in this case if it's layered, the layer above and the layer below. And that may be restrictive if you have a component that needs to interact with three other components, then you are going to have to put in some hacks to talk to the third component via the other two. Okay, so that's not a good way to write a kernel. Okay. Now that said, we said there's one piece of the kernel that actually uses the layered approach, and that's the network subsystem. Okay? And the reason for using the layered approach there is the layered approach maps nicely to what is called the network protocol stack. If you heard the term TCP/IP, okay, the TCP/IP is a network protocol stack. We'll look at this when we talk about distributed systems and networking. Okay, and so you have layers in a protocol stack. Each layer maps nicely to the layered approach. Okay, so if you look at the network subsystem of any OS kernel, that part of the kernel uses the layered approach, not the whole kernel. Okay? Because that part is best implemented using a layered approach. Okay, so that was layered design. Then we looked at microkernels. Okay, so if you remember, in a microkernel architecture, your kernel is essentially a bare bones stripped down kernel. Okay? It only implements protection and communication between other components. Okay? Everything else that you normally associate with the OS kernel is actually implemented as user processes or system processes. So you take the file system, it runs as a regular application. You take the memory manager, it runs as a regular application, and these applications, which are really part of the OS functionality, communicate with one another through the microkernel. Okay? So you pulled pieces of the kernel out and you implemented them as user processes. Okay? And we said this makes it tremendously modular because each component is now its own application. If you want to make changes, you only make changes to that application. So long as the interface is unchanged, everything else should work, okay, as is. Okay, so good improvements in modularity. But the issue with microkernels is it has performance limitations. When one part of the kernel needs to communicate or interact with another part of the kernel. In monolithic architecture, that was function calls. Here, each process is actually sending messages to some other process. That is much more expensive than making the function calls. Okay? So you take a big performance hit when you implement a microkernel architecture. But from many other perspectives, security, modularity, this is a good architecture to stick with. Okay? And the last one was the modular approach, which tries to balance the advantages of the monolithic and the microkernel. So what happens in the modular kernel architecture is you write your OS pieces as modules. Okay, when you write it as if it was an independent module that's independent of others. You just use our API that the OS has provided to you. Okay? So it looks like a microkernel approach in that each function component is implemented as a one or more modules. Okay? But when you boot up the kernels, all the modules are imported by the main kernel and made part of the same address space. So at execution time, a modular kernel runs like a monolithic kernel. Everything is part of one address space. Modules just call functions from one another. But from an implementation standpoint, when you write the code, it looks like a microkernel architecture because each module is independent of others. You write it separately. So long as you follow the API guidelines, it should work exactly without knowing what other modules exist. Okay? So it looks like monolithic when you run, but it looks like microkernel in its modularity when you write the code. Okay? So it tries to achieve a balance in that sense. Okay? So those were the four architectures for OS kernels. Any questions here? Yes, question.
Are there any downsides to the modular approach?
Okay, are there any downsides to modular approach? So the downsides might be some of the downsides you see in the monolithic kernel. If one component has a bug and it's compromised, you can get access to the entire kernel. For example, security would be a downside because in a microkernel architecture, you can compromise one component, but it doesn't give you direct access to other components, except through the API. So here you will have that issue. Yes.
So
Can you repeat your question? Why is it more secure?
Yeah, why is it more secure? Isn't it like the file system now at user level instead of kernel level, which more things on user level?
Yeah, so putting things in user level doesn't make things less secure. Okay, so I think the security is simply comes from if you exploit a bug in one part of the kernel to access, let's say, another part of the kernel. Let's say you are trying to access the memory of a browser because somebody is logged in to their online banking system and the password is cached in their SIP. I'm just making up an example on the fly. Now, the way you will do that is if you get access to the memory manager of the OS, you can figure out where the memory page resides and go and access it. Because now, if you are part of the kernel, you have access to memory directly. Okay? Now, in a microkernel architecture, you could have a bug in the file system process, which you could use to gain access to the file system process, but that doesn't let you get access to the memory manager. Okay? In a monolithic kernel, if you have any entry door anywhere in the kernel, you get access to the whole kernel. So you could use the same file system bug, get access to the kernel. Okay, now you have access to all the memory part of the code of the kernel and you can do what I just said. Okay? So that's an example. So it is simply providing more isolation. It doesn't reduce the number of bugs, but it doesn't let you exploit one bug to harm something else in some other component. That's all it is trying to do. Okay? So more isolation is what you're getting. Any other questions on this? Okay, so those were the first 3 lectures of the course. Then we started talking about processes and thread. That was a sequence of another 3 or so lectures. So as part of that sequence of lectures, we defined what is a process. A process is basically execution context of a program. The program is code that resides on disk. When you execute a program, you load it into memory and you get a process. The process is not the same as a program. Process is an executing state of a program, executing context of a program. Okay? So you need to understand what that is. We define this kernel data structure called a process control block. Okay? Key data structure maintained by any kernel. Okay, what a process control block does is it has a set of entries, one for each process in the system that's active. It tracks everything that the OS needs to know about the process. Okay? That includes the owner of the process, where in memory is the process loaded, maybe the CPU scheduling parameters of the process. It also keeps track of the state of the process when the process is not executing. All the registers are stored in the process control block, okay? So that they can be restored when the process resumes execution. So anything that the OS needs to do for this process, okay, and it needs to know about the process, is stored in the process control block. Okay? So and when we do memory management, eventually you will see that there are a lot more entries in the process control block, such as page tables and so on, which we have not yet seen at this point. Okay? So that's what is a PCB, or a process control block. So you need to know what it is and what it is used for. Okay, and then we looked at the execution states of a process. And we said that a process can be in one of several states, namely new, ready, running, waiting, and terminated. Okay? The state of a process indicates what it is doing at any given point in time. Okay? When you start up a new process, it's in the new state, which means that OS is setting it up, it's loading it in memory and so on. Okay? And then when it's actually gone past the new state, typically it's in one of 3 states. It's in the wait state if it's doing IO and is blocked, waiting for IO to complete. It's in ready state if it's waiting for some time on the CPU to execute, and it's in running state if it's actually executing the CPU. Typically, you'll cycle between these states. If you do IO, you'll go to the wait state. Once you're done with IO, you'll come back to ready state. The CPU scheduler will eventually schedule the process. You go into running state. Time flies expires, you go back to ready state. Okay, and then you can cycle between these things. Once you're done, you go to terminate. Okay, so you need to know these states. Okay? Given any process, some small pseudocode for a process, you need to actually trace what state transitions it makes, given the state transition diagram for these the processes. We will do some examples of that sort of class. Okay? So that's execution states of a process. Okay? Then we introduce this notion of a context switch. Okay? The context switch is an operation that the OS kernel performs to switch from one process to another. Okay? and it involves saving the state of the process that is being evicted from the CPU. All of its registers are stored in the process control block. Okay? And loading the state of the new process, or not the new, but the next process that is going to run on the CPU. Because you look at its TCP, you take all of its registers, you load them, load the program counter, and then it starts executing from where it left off. Okay? So this is a context switch, saving the state of a process and loading the state of the new process that's going to execute. Okay? So you need to understand what is going on during a context switch, the saving and restoring state. Okay? Now, there are many reasons why a context switch may occur. Okay? A process that will be executing may decide to do I/O. Okay? In this case, it is blocked on I/O, so there is no reason to let it run on the CPU. It's not going to be able to execute anything. So you can context switch to another ready process at that point. Okay? Or the time slice of a process may end. So you now have to suspend execution of that process, save its state, resume execution of another process. Okay? Or you may block on the synchronization primitive. When we did this, we hadn't done synchronization, but now we have. So if you do lock acquire and you block, okay? So now you have to basically, you can't run anymore. So that's also going to result in a context switch. Okay, so any of these events may cause a context switch to occur. Okay, any questions? Yes.
For number 4, so the OST track process through this scheduler.
OST keeps track of processes, so the process control. Scheduler is simply deciding which process gets to run. Okay, the process control block is tracking everything the OS needs to know about the process. Okay, so it's a data structure that's tracking everything. Any questions on this? What we just said, context switches. Okay, so then we started talking about threads. Okay, so you will encounter threads very soon in your next lab if you haven't done threads programming, but at least you should know from the lectures what is a thread. A thread is an execution stream through an address space. Okay? When we say a process, technically we are talking about an address space with one execution thread, executing thread within that process. In other words, a traditional process is a single threaded process. Okay? You can have multi-threaded processes where that address space has multiple threads executing through it. Okay? Each thread is executing a part of that code of that process. Okay? So you can have many threads, each of which could be executing arbitrary pieces of code all concurrently. Okay? Each thread gets its own stack, it gets its own register, it gets its own program counter, but they share everything else. They share the code, they share the heap. Okay? So we looked at what is a thread and why we need threads. Okay, threads allow you to implement concurrency within an address space, within a process. Okay? So you can have different parts of the process executing concurrently. That's what threads will allow you to do. And then we looked at how you go about implementing threads. We looked at two different ways to do it, a kernel level thread and a user level thread. Okay? A kernel level thread is a thread that the kernel knows about. Kernel provides explicit support for implementing threading in this case, in case of kernel level threads. Okay. User level threads are threads that are implemented by a library. Okay, they are transparent to the kernel. The kernel does not know about the presence of threads. In this case, they are managed by user libraries. Okay. And we looked at advantages and disadvantages. We said kernel level threads, the kernel will know when there are multiple threads in a process, it can give them more CPU time and so on. Okay. In a user level threads context, you will not know. Okay. That there are multiple. They look like a traditional process. You schedule the process, the user level threads library will run its own scheduler and pick a thread to it. Okay. Scheduling is a two-step process when you're user level. CPU picks a process to run, the user library then picks a thread within that process to run. There are two steps to schedule. The kernel level thread, the CPU directly picks which thread to run for a process. Okay, there's nothing else you need to do. Okay. And there are advantages and disadvantages. User level threads are more efficient because they don't involve system calls. They're all function calls to a library which is much faster. Okay, so and you have more flexibility because you can implement whatever thread scheduler you want. You don't have to be bound by what the CPU scheduler is doing. The CPU scheduler uses MLFQ. The thread scheduler can pick some other policy, whatever it wants. Okay, so you get more flexibility in that regard. The kernel level thread scenario, you are actually stuck with whatever the CPU scheduler is doing, whatever policy it has chosen, is what is going to be used for your threads as well. Okay. Now, so that's the disadvantage, but on the flip side, the advantage of kernel level threads is the kernel can see the threads within a process. So one process has 100 threads and another process has 10 threads. You can actually schedule more of the threads from the first process and give it more CPU time, as you should from a fairness perspective. Okay, in the user level threads package, you are don't have visibility into what's inside the process. You don't know how many threads are in there. Okay, so you cannot do anything like that. Okay. And in the user level threads application or process rather, when one thread blocks, everything blocks. The entire process is going to be. The kernel level threads system, if one thread of a process blocks, only that thread blocks. The other threads are handled independently by the kernel. Okay, that's an advantage because you can actually get more concurrency even when some threads are blocked, other threads cannot. In user level threads package, one thread is blocked, everything is stuck because you don't know about the presence of other threads. Yeah, that's a downside to user level. Yes, question.
So in summary, if we use user thread for multi-core processing.
You should not use user level threads for multi-core processes because multi-core systems rather because user level threads will not give you true parallelism. In the kernel level threads, you can take two threads belonging to the same process, schedule them on two cores at the same time. In a user level threads package, you can only schedule the process once. You don't even know of the presence of the thread. So you cannot actually schedule it twice.
So in which scenario should we use user level?
Well, each scenario is a different problem. So typically you may be stuck with whatever your system is allowing you to do. Your OS doesn't support threads and you want threading, you have to pick a user level threads library. Your kernel supports threads and your system supports thread, then you are fine. So typically this is not an application programmer decision. This is a decision of the runtime system. If you are implementing a threading packet, that's the question you should ask. Should I use kernel level or user level? Not from an application standpoint. If the kernel supports it, you use kernel to implement your threading. It's not you use user level packages.
In the discussion section, there was a question about, so you have a lot of threads,
Okay.
a large amount of threads, which kernel should you use?
Which system should you use?
Which kind of kernel, no, kind of threads should you use? You have a large amount.
It doesn't matter if you have lots of threads. It depends on what you're trying to achieve. If you want your own policy, you should pick user level threads. If you want true parallelism, you should use kernel level. There is no answer to the question that if you have lots of threads, which one should you use? The answer is it would depend on what your goals are. Do you want to implement true parallelism? Do you want maximum efficiency? In which case you shouldn't use kernel level threads, you should use more efficient user level threads. Okay, so you can pick any advantage of any of those and say, that is what I was trying to achieve, I would use it for that reason. Okay, there's no one answer to that question.
Why is user level thread more efficient if it cannot run parallel?
It's more efficient because all thread management calls are library calls, not system calls. So if you, for thread creation, thread deletion, it will be much faster than using kernel level threads. Okay, any other questions on threading? Alright, so next is process creation. We looked at fork and exec, which you have used extensively by now, hopefully for lab 1. So you know what they do. Okay, so fork is a system call that you can, any process can invoke that makes a child process, which is an image or mirror image of the parent process. Okay? Fork is going to return the process ID in the parent, is going to return 0 in the child. Once you created the child process is free to do what it wants. Okay, it can execute the parent's code, or you can call exec to execute some other program within that child process. You call exec, that program is going to replace the contents of whatever the process currently has. It will start executing the child program. So basically, you need to understand what fork is, what exec is, and understand how to create child processes. If you remember, I put up a template in the lecture. It said call a fork, and then you check the return value of the fork, and say if the return value is 0, okay, then you have write a child code in there, and then in the else part you write the parent code. Okay, so you basically, if you use that template, you will always end up with the correct code for writing fork and exec programs. Okay. So you could be asked things like have a process create 3 other child processes, or have a process create a child, have a child create a grandchild. So you need to be able to write the structure of the code that would achieve that process hierarchy. Okay, and if you use that if-else structure recursively in the right places, you can get whatever behavior you want in terms of creating process hierarchies. Okay, is that clear? Any question there? Okay, so that's processes, threads, and then the last topic, well, not the last, but second to last topic is CPU scheduling. We covered quite a few different policies there. Okay. First come, first serve, round robin, shortest job first, MLFQ, which is multi-level feedback queue, and largely scheduling. So you need to know all of those policies. Okay. You need to know which ones are preemptive and which ones are non-preemptive. Okay. Preemptive ones are policies that actually use time slices, and you can preempt a process when this time slice expires and run some other process. Okay, non-preemptive policies are policies that once the CPU scheduler picks a process, that process either gets to run to completion or it gets to run until it does I/O or synchronization and blocks. Okay, so in a non-preemptive policy, you cannot preempt a process. You cannot evict a process once it started running. The process has to give up the CPU. Okay, in a preemptive policy, either the process gives up the CPU or you can force the process to give up the CPU when its time slice expires. Okay? So some policies are preemptive, others are not. FCFS is an example of a non-preemptive policy. The shortest job first is an example of a non-preemptive policy. A round robin policy uses time slices, so it's preemptive. A multi-level feedback queue is also a preemptive policy. Yeah, and this lottery scheduling. Okay, so you need to understand what these policies are, which ones are preemptive, which ones are not. Okay, you need to also be able to work with the examples such as the ones that are in the homework, where you have some jobs have certain lengths, and you're given a policy and say work through that policy. Right? What are the completion times, what are the wait times, and so on. Okay, we did several such examples in the class. Okay, so you should understand all of those. And then we also looked at the notion of a quantum or a time slice, which preemptive policies use. That's the duration for which a process is given the CPU whenever it is scheduled for execution. Okay? The length of the time slice determines how much time this process can run before it is evicted by the OS schedule. Okay? And we looked at trade-offs in picking a good time slice duration. We said if you make it large, there are fewer context switches. That's good, because context switches are tax we have to pay to switch between one process to another. It's an overhead. Okay? So making the time slice large implies you have fewer context switches. Okay? But making the time slice large also implies you have higher wait times. Okay? Because if a process comes in, it has to wait for a long time slice to expire before it even gets a shot at the CPU. And if they still not get it, there are other processes waiting ahead of it. And in contrast, if you have smaller time slices, you are going to run each process, each ready process for shorter periods of time, but you are going to cycle through them quickly. So the wait times reduce when you have smaller time slices. Okay, but the number of context switches go up. So you pay more overhead in terms of context switches, but you have lesser wait times. Okay? So you want to pick something that balances the two. Okay? So you don't want to make it too small and have too many context switches and pay a lot of overhead. Neither do you want to make it too large and too coarse-grained where you're going to have a long wait time. So typically, you have time slices that are in the order of a millisecond to tens or 100 milliseconds, hundreds of milliseconds. Okay, so that's a rough range. Different kernels make their own decisions. So there's no one time slice that is good for every kernel. But by and large, if you look at most of the OS kernels, you'll have some that pick a millisecond or a few milliseconds. Linux uses a 20 millisecond or 200 millisecond time slice. Okay? Some other operating systems use maybe tens of milliseconds. Okay, so that's a rough range, and you will see. Okay. And then we looked at also this notion of I/O bound and CPU bound processes and why we should give priority to I/O bound processes. Okay, we said I/O bound processes spend most of their time doing I/O with short periods of computation between two I/Os. Okay? So when I/O bound process becomes ready to run, it is better to run it quickly and then it will give up the CPU quickly and go back to doing I/O. So then it doesn't have to wait for the CPU. Okay? So our strategy was give priority to I/O bound tasks so that they can quickly run and then go back to doing I/O. And then give lower priority to CPU bound tasks. So once the I/O bound tasks are done, then your CPU is all available to run these long CPU bound tasks. Okay, so then you can run your CPU bound tasks once you finish doing the I/O bound. So that was the strategy, and the same strategy used in MLFQ, multi-level feedback queue, where we said I/O bound tasks are typically given higher priority. You look at the behavior of the process within a quantum to decide whether it's I/O bound or CPU bound. If it's I/O bound, which means it gave up the CPU in the middle of its time slice, we keep increasing its priority. If it uses its entire time slice, we drop in priority. Okay, so we treat I/O bound and CPU bound tasks differently in MLFQ and give or favor I/O bound tasks over CPU bound tasks. Okay, so you need to understand why that's a good strategy and then how to implement it in the context of MLFQ. So, yes, question.
So when we calculate the waiting time for the jobs,
Yeah.
do we include the I/O time?
Okay. Question is when you compute the wait time for the job, you include the I/O time. Okay, you should. So wait. You can wait for any number of reasons. The thing you should realize is processes will wait for different reasons. You may be waiting for I/O to finish. That's wait. You may be waiting to acquire a law. That's wait. You may be waiting. You may be in the ready queue waiting for the CPU. That's also wait. Okay. So when you are broadly told what's wait time, wait time should be any time you are not computing is all wait time, or not executing is all wait time. Okay, the wait may be happening for different reasons, but it's all waiting. So in this case, the answer would be yes. You should include waiting.
So suppose there's a job that does I/O after 1 second.
Yes.
Is the so the CPU job time is 5 seconds. So after the last seconds of CPU time, does it still do the last one?
You always have to finish when you're computing. You can't do I/O and finish when you have to execute something.
I mean,
So I'm not following what you're asking.
so if the job does I/O once after, if the job does I/O after every second,
Yes.
so does it do I/O in the last second? After it's finished,
I mean, you're asking an abstract question. I mean, typically you will be given a scenario and you just follow what the scenario tells you. If you're asking, can a job finish after it's finished I/O, the answer would be no. Because after it finishes I/O, it still has to run, get the results of the I/O and then terminate.
I mean, when it finishes the CPU time, does it still do I/O?
I don't understand your question. Why don't you come back after the class? Because what you're asking is not making sense.
Sorry.
Okay. Yes, your question.
Will homework one answers be posted before Thursday?
Homework one answers, I will try to get it posted. We just came in yesterday. I tell the TA to put it up today.
Okay.
How about the discussion worksheets?
This, the actual worksheets or the solutions to the worksheets, or both? So they, as I showed the other day, they are actually on the course webpage. They should have been mirrored or moved. Have they not appeared yet? Because I post them the week or maybe a few days after they are actually held. I will make sure they are there. They are actually on the course webpage. They have been there for a long time. I will make sure they get up. In fact, the solutions are also put up there. Okay? Any other questions? So homework one solution we put up. And then discussion, I think they're already there. I checked that they're also cross-linked to Moodle. Okay, so let's finish this up and then. Okay, so last topic was synchronization. So you need to understand all of the key terms there. What is synchronization? What is mutual exclusion? What is critical section? Okay, so mutual exclusion is the ability to exclude other processes or let's say threads, other threads from doing something when some thread is actually holding a lock, let's say. Okay? So you exclude other processes from doing something. That's called mutual exclusion. The critical section is a piece of code which, if one thread is executing, it blocks other threads from executing that piece of code. And typically, when you put a lock around some piece of code, that code becomes a critical section because you have to acquire the lock to execute that code. And once you acquire the lock, other processes are blocked from acquiring the lock, so they can't execute that code. Okay, so you should understand the notion of synchronization, where the mutual exclusion and critical section. These are three terms that are sort of central to this whole notion of problems of synchronization. Yes, question?
Wait, is the critical section defined as if it involves shared memory, or is it defined as if you need a lock to get it?
No, so neither. Critical section is simply a piece of code which, when one thread is executing, it prevents other threads from executing that piece of code. That's what a critical section is. It's a piece of code that is that only one thread can execute at any given time. You implement a critical section using a lock. Okay, so locks allow you to implement a critical section. Critical section is simply a piece of code that only one thread can execute. That's what it means.
So you can implement a critical section somewhere where it doesn't need to be. Like, if you can do like an unnecessary critical section.
You can implement
You can
the
put a lock
critical
wherever, and then it becomes a. If you were to put a lock on a piece of code, it would be a critical section,
Yes.
no matter what the code is.
Yes. Yes, essentially. Any code that is guarded by a lock or semaphore that work like locks or monitors are critical sections because they meet the definition, which is if one thread is executing it, it can prevent other threads from executing. Okay. Any other questions here on the definitions? Okay. So then,
Wouldn't a critical section be where you're introducing volatility into the code? So like if you have a particular variable that you're accessing, and you have a bunch of processes or threads running at the same time, they could all access this variable, excuse me, and then just, by accessing and changing the variable, then change the operation of various other processes.
yes, but I didn't understand the question. You explain the scenario, and what's the question? So you
Just
said
like
there are processes.
the presence of a lock doesn't necessarily make it a critical section. It's just a critical section because if two processes access at the same time,
Yeah.
it can ruin the execution of the code.
Right. So here is a piece of code. Doesn't matter what it is. So you just say there's some instructions. So if you say you do this around this, this becomes a critical section. Okay. Now you are asking if there are some. Here is a variable. If there are many threads accessing it.
Is that the only definition of a critical section? That it just needs to have lock around it and then it's a critical section? That's it?
No, so the definition of a critical, you are confusing the implementation of a critical section from a definition of a critical section. The definition of a critical section is it's a piece of code which one thread is executing, it prevents other threads from executing. Only any code that only one thread can execute at any given time. That's how it's defined. You can implement, one way to implement it is a lock, because locks prevent other threads from executing that piece of code. You can also implement it as a monitor, you can implement it as a semaphore. Okay. There could be many other ways to do it. You can disable it, you can do all sorts of other things. Okay. So definition simply says it's any code that only one thread can execute at any given time. Other threads cannot execute it if some thread is executed. Okay. The common way to implement it is a lock. So now I didn't follow the question you are asking about shared variables and so on. Does that answer the question?
Yeah.
Yes.
So just to clarify, it's defined not by a section in code that should, like from an abstract perspective, should be separated from all other threads, but defined by what actually is separated from all other threads in a clear
Yes.
program.
So it's not saying that here is your application, so this part should be protected.
Okay.
That's your design of the application. It is simply an abstract concept saying any code that only allows one thread to execute is called a critical section. Now, you should ask the question when you write some application, which part should become critical section, because those are the ones that are shared variables and so on. Okay, it doesn't tell you what to do, it only says what it is. Any questions on this? Alright, so we looked at, actually looked at 3 primitives, but we only have 2 in the test. The monitors are lecture after lecture 8, so I can remove monitors from that, I put it on the review. So we looked at a lock, we looked at semaphores. Okay, so we looked at, so lock, as you know, has 2 primitives, lock acquire, lock release, and that's what you use to implement synchronization. So we saw how to implement locks using this notion of test and set assembly instruction. Okay, it's an assembly instruction that allows you to get the value of a variable and set it in a single assembly instruction. It's an atomic instruction, and it is what is used internally to implement a locking library, or it's used to implement locks at the kernel level. You can also use enabling and disabling interrupts, which is another hardware feature to implement this. So you need to understand both aspects, how to use locks, how to implement locks. So internally, if you're a library designer, then go implement a locking library. How do you do that? Because that requires you to understand test and set and interrupt. Okay? And then if you want to write a synchronization code that uses synchronization, that's how to use locks. Okay? So you need to know where to put lock acquire, how to put lock release, and so on and so forth. So that you need to understand both of those issues. Okay? Same with semaphores. The same is true of semaphores. You need to understand what are semaphores. Okay, so they are special variables that you can increment and decrement using 2 methods called wait and signal. Okay. Wait decrements the value of a semaphore, and if the value goes negative or is already negative, it causes that thread to block. That's the definition of wait. The signal increments the value, and if the value is still negative or 0, it unblocks any thread that is waiting. So signal is going to increment and let any of the waiting, one of the waiting threads to resume execution. Wait is going to decrement, and if the value goes negative, it will block the thread that calls wait. That's the definition of wait and signal. Okay, so we looked at how to use semaphore. We said there are 2, in particular, there are 2 different reasons, not reasons, but 2 or 3 different ways to use semaphore. One is called a mutex semaphore, same as a lock, also called binary semaphore. Okay, so in this case, semaphores is simply being used as lock. Another one is called counting semaphores. The counting semaphores allow you to initialize the value of the semaphore to n, and it allows n accesses to a data structure. If you have multiple instances, let's say you have a bank of printers, you need to grab a lock of the printer to send a print job. If you have a bank of n, you can then basically initialize this. You can either protect each of those printers by a semaphore, or you can protect the entire bank using a counting semaphore that protects all n of them, and it allows n processes to print, and then the n plus 1 processes to wait to print its job. Okay, so that's called a counting semaphore. And then the last use of semaphores was to implement what we call scheduling constraints. Okay? In this case, the semaphore is initialized to 0. This causes some process or thread to block. Okay? Another process can wake it up using signal. We looked at the producers and consumer problem, and we said if the producer or a consumer runs first and there's nothing to consume, it blocks on a semaphore. When the producer runs and it produces the data item, it will unblock the consumer. Okay, so you can use semaphores also to block and unblock threads. Okay, so that's the third use of a semaphore. So you should understand these 3 distinct uses. One is use it as a normal lock. The another one is to use it as a generalized version of a lock where you protect n resources. The third one is to ensure some scheduling operations. Order with processes. Now, in this context, we also encounter this term busy wait. Busy waiting simply means that you are waiting in a loop, waiting for some condition to become true. Condition is false, you keep checking the condition. So while this condition stays false, loop. Okay, you're just sitting and looping there doing nothing. Okay, so this typically means you waste CPU cycles sitting in a loop, not doing anything useful. Okay. But there are many reasons to have busy waits, but ideally you should have as little busy waiting as possible because it wastes CPU cycles. In particular are implementations of semaphores and locks all involve some degree of busy waiting using a test and set instruction. Okay, so we looked at some simple implementations that involve lots of busy wait and more complicated implementations that reduce the amount of busy wait. So you should go and understand what is busy wait and you see how we use them to implement locking. Okay. Then we also, I already mentioned interrupts and test and set and so on. So those are all ways by which you implement these synchronization primitives. Okay, so the last thing here is you should, as I said, you could get design questions and here is the problem. You will go use locks to implement some scenario. So we looked at some simple examples in the class. You may get some simple ones like that on the test. So you should be able to write pseudocode. You don't have to write code that compiles on the test or anything like that. Any code that you are asked to write can be pseudocode. You just need to get the logic right. Okay, so it's more important to understand the design of your code than to look at the syntax of your code. Okay? Any questions on this? So that's basically a quick, not really quick, we spent 45 minutes. Yes.
Seems like there's a blank there.
Yeah, the blanks you said monitors you said took out because not on the test. So I said all synchronization and I realized that monitors are not because I said lectures 1 to 8. Between monitors and lecture 1. Yes.
So there will be no reader, right?
There will be no reader writer problem. Correct. Because that came after lecture 8. Then go and look at the first 8 lectures. That's the only thing you need to really worry about for this test. Second test, different problem. You have to worry about readers, writers. Okay. Any other questions here? Alright, so we are not done with the class. So there are two things. I want to actually start some material on deadlocks, which I will. Okay, so you'll have to bear with me. You may have the exam on your mind, but we will start a new topic quickly. Okay, so that's one thing that I'm going to do for the rest of the class, next 30 minutes. The other thing I wanted to ask was maybe I'm thinking it's not a good idea to have a lecture on Thursday. I was planning to, but I feel like you may not be in the mood to learn about yet another topic. So I may end up cancelling that lecture and instead I'll come to the discussion on Friday and just turn that into a shorter lecture. Because there isn't much to discuss. We just turned in a lab. Lab 2 is not out yet. So there isn't a whole lot to do in the discussion, so I could just do that. So would you rather have me have the lecture and cancel the discussion or cancel the lecture on the day of the test and have a discussion which is actually a lecture? So I'll cancel the lecture. I like that better. Yes, alright. So there's no class on Thursday. I'm going to email that out. Okay, but there will be a discussion which will be a lecture. Okay, so with that, let me spend a little bit of time talking about deadlocks. We may not get through a lot of this material today. So I'll just introduce what they are and then give you some examples of why they occur. Okay, so here is the real slide you really need to know about what is deadlock. Okay. So deadlock is a condition where a group of threads is waiting for an event that only that group can generate. Okay. Typically, what happens, typically the reasons you have deadlock is that the event you are waiting for is you are trying to acquire a lock or a semaphore and you are blocked on it and some other thread in that group holds it. Okay. And here is sort of the canonical example of a deadlock. So you have process A and process B. There could be thread A and thread B. Doesn't matter. Okay, so you are trying to lock the printer and lock the disk. Let's say each of these processes is trying to print. So you are trying to grab a lock on your file and send that file to our printer. So I will assume that both are shared resources. So you are going to grab a lock on the printer, grab a lock on the disk. And process A tries to get the printer lock first and then the disk lock. And process B gets the disk lock first and the printer lock. Okay, so they just try to acquire the same lock but in two different orders. So one is getting the they are trying to grab the printer lock, the other is going to grab the disk lock. So now if you look at this code carefully, you will see that there will be many scenarios where something bad may happen. And here is an example. Process A runs and grabs the printer lock Okay, it acquires that lock, but before it can grab the disk lock, its time slice expires. Okay, so now process B runs, okay, and it grabs the disk lock, which process A hasn't yet grabbed. So the disk lock is available, so it gets the disk lock. And before it grabs the printer lock, its time slice expires. So now each process is holding one lock. It hasn't yet grabbed the second one. So now process A is going to run next. It's going to ask for the disk lock, which process B has already gotten. So it will block, waiting for B to release that lock. Now process B will run, and it's going to ask for the printer lock, which A holds. It will block. Now these processes are going to block forever because each of them hold one lock and they're waiting for the other lock with the other process holds. Okay, so now you'll have one condition called a deadlock because there's no way to get these processes to make any progress. They are each holding a resource and waiting for another resource by the other process holds. So they're waiting on one another. You wait on one another, nothing can happen in the system. Okay, is that clear? That's an example of a deadlock. So you are holding some resources and waiting for other resources that some other thread in that group holds. Okay, this is a classic condition of a deadlock. So if you write this kind of code, you are going to have problems. Okay, so it looks fairly innocuous when you look at it, and you're just grabbing two locks. But because you did it in a certain order, which was the wrong thing to do, you got yourself into trouble. These processes got themselves into trouble. They are deadlocked. Okay. Now you should also realize that this may not always happen. Okay. The scheduling order I have actually just explained will only occur rarely. Okay. That doesn't mean that there is no bug in the code. Okay. So at some point in time you're deadlocked, you still have a bug. Many times these processes may run fine. They may just grab the two locks, quickly print, and then the other process runs. It will grab both locks and run, and everything is fine. Doesn't mean this has to always happen. Okay. But if it can happen because of a certain order of scheduling, then your code has a bug. Okay? And it's going to be a bad, nasty bug. It will only occur once in a while, okay? But it still has a bug. Okay, so let's now go through some terminology, and then I'm going to show you some more examples of how you can actually address this kind of scenario. Okay? So a deadlock, as I said, requires multiple threads. Some threads hold some resources, wait for other resources, and so on. Okay? And we look at two different techniques to address deadlock. Okay, we look at what is called deadlock prevention, where your code is actually going to do extra checks to ensure you don't actually do anything that is going to make put you in what is called an unsafe state. So whenever you get requests to acquire locks and so on, you are going to run some extra checks saying, if you granted that request, could there be a potential deadlock down the road? Okay, you are going to do this runtime check. And you may actually not grant a log that is still available if it could result in a potential deadlock. And these kind of techniques are called deadlock prevention. Okay? So they do run the checks before the fact and try to prevent the system from getting into a deadlock. Okay, then the other class of techniques is called deadlock detection. These are after the fact techniques. Every once in a while you run some checks to see are there some processes that are deadlocked and they are just stuck. Okay, so if you find any such processes, you terminate them because there's nothing you can do for them. Okay? So either you do checks before the fact, before the deadlocks occur, and try to prevent the system from getting into a deadlock, or you let the processes run, do whatever they want, but every once in a while you run checks post fact only. Are there some processes that seem to be blocked and doing nothing? Have they gotten themselves into a deadlock? If yes, if your test says yes, then you basically have to terminate them. Some of them or all of them. So we'll see both classes of techniques. One that do checks after the fact to detect a deadlock after it has occurred. The others that do checks before to prevent the system from getting into a deadlock in the first place. Okay, these are the two scenarios we are going to look at. Okay? And then the last point here is to understand that deadlock is not the same as starvation. We encountered starvation already multiple times. Okay, when we said this, we are favoring short jobs or long jobs can starve, and we looked at many scenarios. In the reader-writer problem, we looked at scenarios where readers can starve out writers. Okay? So deadlocks are not the same as starvation. In starvation, you have some threads that are waiting, and they will wait indefinitely, but other threads are actually making progress. Okay? The short jobs are getting scheduled and they're starving the long jobs. but at least the short jobs are making progress. Okay? In deadlocks, no one makes progress. Okay? In starvation, some threads make progress at the expense of other threads. Okay, so there are two different scenarios. In deadlocks, nothing makes progress, everything is blocked. All threads are blocked. In starvation is a condition where some threads seem to be blocked, not making progress, okay, but other threads are actually making progress. Okay, so you should understand that it's different. They are not the one and the same thing. Any questions on this? Okay. Alright, so I'm going to now describe these four conditions which are referred to as necessary conditions for a deadlock. Okay. So what the necessary condition means is if there is a deadlock in the system, all four of those things are true in that system. Okay, so you should know what a necessary and sufficient condition is, I hope. Okay, we should have done this in 311 or 230 or 240. Yes? Not 230, 240 or 250. So sufficient condition says if those conditions are true, then you get a deadlock. I'm just saying these are necessary conditions. In fact, I will argue or tell you that they are not sufficient, they are only necessary. So what that simply means is if you find a system with a deadlock, then all four of those things are true in that system. Okay? And what are those four things? The first is mutual exclusion. That means that there are threads that are trying to acquire locks. Okay? If you don't have any locking code, you will not have deadlocks to begin with. It doesn't even arise. The issue of deadlock doesn't arise if you have threads that don't have any locks in them. Okay? So clearly, if there's been a deadlock, then you had code that tries to do locking or semaphore or something along those lines, which means you have mutual exclusion. The other condition that is true now is what is called hold and wait, which essentially says each thread is holding some resources and waiting for some other resources that other threads are holding. Okay, so in the printer in this case, one thread held the printer lock and was waiting for the disk lock. Other thread held the disk lock and waiting for the printer lock. Okay, so you're holding some resources, you're waiting for some other resources. Okay, that's called hold and wait. Okay, so hold and wait must be true. Okay, the no preemption case must be true, which is that if a deadlock has occurred, you are not actually allowed to preempt any resources from the threads that are holding them. Okay, if you could, then you would not have a scenario like that. Preempting resources simply means I take the lock away from you forcibly. Okay? Until now, we assume that if you acquire a lock, it's your responsibility, that thread's responsibility to release the lock. There was no notion of the system just forcibly took the lock away, saying, too bad you had the lock, I'm taking it back. There was no such scenario. Right? So that means you have no preemption. You're not allowed to forcibly take resources some thread is holding. That should also be true. Because if you could, any thread that's blocked, you can just take those resources away. Okay? And the last and sort of most important condition is what is called circular wait. Okay, which basically says there's a group of threads, each of them is waiting on another thread, and you see a cycle. Okay, meaning thread 1 waits on 2, 2 waits on 3, 3 waits back on 1. So now you have a cycle. Okay. In our 2-thread example, the cycle is obvious. Okay, thread A was waiting on B, B was waiting on A, so you had a cycle. Okay. So you don't necessarily need 2 threads. You can have any number of threads. In particular, you have n threads. Okay. And you can order them so that each is waiting on the next one, and you can basically see a cycle. Right? And then if you have a cycle, if you have a deadlock, then there is a cycle somewhere. Okay, that's basically your hold and wait cycle. Okay, so all 4 of these conditions are going to be true when there is a deadlock in the system, and this is why it's called necessary condition. Okay, so you need to understand all 4 of them, in particular the last one, which is what we are going to focus the most. Okay, so here is an example of a cycle that I'm going to show you, but before I show you that, I'm going to define what is the cycle on. Okay, so this picture here is referred to as the resource allocation graph. Okay? The picture, that graph, has 2 kinds of entities. There are threads and there are resources. The square boxes are resources, labeled R1, R2, R3. What the resources are is not really important. Okay? It could be disks, printers, but here we are going to just use abstract resources and just number them. Okay? The circles are threads, okay? T1, T2, T3, T4. Okay, so you have some resources and some threads. Okay, so the circles are threads, the squares are resources. and there are directed edges in this graph. Okay? There are two kinds of edges. Okay? What is called a request edge and what's called an assignment edge. Okay? So when a thread goes from a thread, edge goes from a thread to a resource, like this thread T2 as an edge going to R1, that means that thread is requesting that resource. It is asking for the resource, it's trying to grab a lock on that resource. Okay? That's called a request edge. You make a request for a lock. Okay? The assignment edge is the opposite. You have edges going from resources to threads. So here you have directed edge that's going from a square box to a circle, okay, which is the opposite of this. So what that tells you is this resource is currently held by that thread. That thread holds the lock on that resource. Okay? So the request means I ask for a lock. An assignment means I hold the lock. Okay?
All the resources have like mutual exclusion, right?
Yes, every resource will assume is protected by a lock. So to ask for it, you're essentially doing lock acquire.
Are we only talking about locks, or does this also apply to like sound force?
This will apply to any synchronization. Just for simplicity, we will pick one because it's easy to understand. It doesn't matter what the synchronization is, but we will just assume locks, but it will apply broadly to any synchronization. Okay. So now you have these kinds of edges here, and you'll see that there is a cycle. The reason there's a cycle is T2 is waiting to get R1, a lock on R1. The lock on R1 is held by T3. T3 is now also requested a lock on R2, which is held by T4. T4 has requested a lock on R3, but the lock on R3 is held by T2. So now you basically got a cycle. It's a directed graph, so there needs to be a cycle with directed edges, okay, not just an undirected cycle. Okay. So each thread is holding a lock. In particular, T2 is holding R3, is asking for R1. T3 is holding R1 and asking for R2 and so on. So now we basically have a hold and wait and a circular wait in particular. Okay, so you see a cycle in the loop. So this is indicator. If there's a deadlock, then this condition should be true. So you should have a scenario like this where you have this resource allocation graph and you see a cycle in that graph. Okay? So if you wanted to do something post facto, you wanted to do deadlock detection, all you need to do is write a cycle detector. Okay, if you've taken 311 or any of these classes, you know how to detect cycles in a graph. Okay? Here's an example of where you use such an algorithm. If you wanted to actually detect whether there's a deadlock, every once in a while you take the resource allocation graph that the OS may maintain and just look for cycles. You know the cycle detector and say, is there a cycle in this graph? If you find a cycle, that's bad. Yeah, it is indicative of a deadlock. If there are no cycles, then guaranteed there is no deadlock. Yeah, because the cycles are a necessary condition. Okay, so no cycles means no deadlock. Okay, deadlock implies cycles. Because if your cycle detector says sorry, there's no cycles, you should say fine. There's no deadlock, there's nothing to do. If you find a cycle, then that's something that you need to address. And is there a deadlock? Should I do something about it? Should I kill some of these processes? Okay, because that's the only way to resolve it. Okay, so one way we are going to actually address this is to just simply take our resource allocation graph and run a cycle detector. Okay? But now I'll also show you an example where just because you found a cycle in the graph doesn't mean that you have a deadlock. Okay? This is why it was a necessary condition, not a sufficient one. Okay? A sufficient condition should have been if I found a deadlock, there's guarantee. If I found a cycle, there's guaranteed deadlock. But that's not what we are saying. We said that if there is a deadlock, there's a cycle. Right? Here's a counter example where I'll show you a cycle, but we'll also convince ourselves that that scenario is not going to result in a deadlock. Okay? This will occur only when you have multiple instances of a resource. There's only one type of each resource, then you will actually get a cycle will actually imply a deadlock. But because you can have multiple resources or multiple instances of a resources that are interchangeable, okay? You may not have a deadlock even if there's a cycle. So an example is if there are 3 printers, okay, I have bank of 3 printers, they're all identical. When I say print, I don't particularly care which printer. So long as it prints on one of them, I am happy. Okay? So if you have a scenario like that, okay, where you have multiple instances of a resource, here I'll show you an example where you will actually have a cycle but not a deadlock. So in particular, this resource allocation graph, you will see that certain resources are multiple instances. There are 2 instances of R3. This could be 2 printers, for example. Okay, that would be 3 instances of R4. This could be tape drives that are using for backup. You just say backup my files. Which tape drives are used, I don't care. So long as you back up my data, I'm happy. Right? So if you have in scenarios like that where you have interchangeable resources, you will not have this case. Okay, here is an example. Okay? You will see that there is a deadlock, or not a deadlock rather, there is a cycle here where R3 is assigned to T2, T2 is requesting R1, okay? R1 is actually held by T3, which is requesting R4, and then which is held by T4, T4 is requesting R3. So there is a cycle in this loop. Okay? Now I'm going to claim that just because there is a cycle, that scenario is not going to indicate a deadlock, because you can actually make progress in the system. Okay? In particular, you'll see that there are 3 instances of R3. Okay? And one of these instances is actually held by T1 at this point in time. So let's say this is a printer and T1 is printing on the printer. Okay? T1 is not part of the cycle in this particular example. Okay? So let's say when T1 is done, okay, it's going to release that instance. Now you can use that instance to make progress in the system. In particular, you can basically give that instance to T4, which was requesting an instance of R3, and now your cycle is gone. Okay, that's basically you just allocated that resource, an extra instance, and you remove them. Okay? So if you have multiple instances of a resource, and there are some instances that are not part of the cycle, you can easily break the cycle just when some of those resources are freed up. You can allocate them to other threads that are part of the cycle and break the cycle. Okay? So this should tell you that just because there is a cycle doesn't mean there's a deadlock. There are sometimes cycles where you can still make progress. So it's not a sufficient condition, it's a necessary condition.
Will the other cycle result in a deadlock?
In this case, you will actually, there is no way to make progress. Okay, this is simply a generalization of the previous case where there's only one instance. Okay? So here, there is no way to make a deadlock progress. Okay? You didn't have multiple instances as a luxury of saying, okay, I'm going to allocate something. Okay? So when you have one instance of a resource, the cycle is very bad. Okay? It is actually going to mean deadlock. There's no way to make progress. So all the resources are in use and they are actually held by other processes. But when you have multiple instances, a cycle is not necessarily a bad thing. You can still make progress. Okay? So what that should tell you is just because your cycle detector found a deadlock doesn't mean it's time to start terminating processes or reboot systems saying, oh, bad things happen, let's reboot and reboot. So there's no need to panic yet. You have to actually analyze the situation more. But if you have only one instance of any resource, then it becomes both necessary and sufficient. Okay, but in the general case where you can arbitrary instances, it's not sufficient, it's only necessary. Meaning if there is a deadlock, there should be a cycle somewhere and no way to make progress. But just because you found a cycle doesn't imply that there's a deadlock. There may be ways to make progress. Okay? So important to understand that when you have multiple resource instances, you may not actually result in a deadlock. So here is a simple thing you can do now with that background. So you essentially scan the resource allocation graph, run the cycle detector, and when you find cycles, okay, so you can say I am going to do something and break those cycles and do something. Okay, so you can kill all the threads in the cycle, you can kill the threads one at a time, force them to give up resources or preempt resources. You have to do something to break the cycle. Okay, which could be kill all the threads is equivalent of I actually terminate them, I restart the system, and all the threads restart. And so they start from scratch, all the cycles are gone. So you have to take some harsh measures once you find a deadlock in the system. And running cycle detectors is not cheap. Okay, if you actually remember cycle detection algorithm, you know that they're order n square algorithm. You have n nodes in a graph. Cycle detection is order n square execution time. Okay, so O of n square. That means it's expensive to run. When you have lots of processes, lots of resources, okay, let's say you have 100 processes and 200 resources and 300 nodes in the graph. So it's order of that. So it's going to keep growing. So you don't want to run this frequently. But you cannot. It's going to be very expensive for the OS to run this every second. So you need to run it infrequently and then find processes that seem to be just sitting there, not making progress. Find the cycle. You find some cycles, you can say, is there a deadlock? Analyze it, and then you find a deadlock, and you can try to break the cycle by terminating processes. Okay. So this is referred to as deadlock detection. Right? So you look for deadlocks after the fact. Okay. So you don't do anything beforehand. You just let processes execute whatever code they want to execute, and then every once in a while do checks. Has anything bad happened in the system? And then correct for it. Okay. So that now, as far as real operating systems go, they don't worry about deadlocks. Okay. So this is all well and good, but this is so expensive to do that the OS says, not my problem. You wrote bad code and you caused a deadlock, you figure it out and you restart your system or do whatever else you need to do, kill your application. So it's left to the application programmer either to implement this or just say something is wrong, I'm going to restart the system or some such thing. Okay? But you could, in theory, implement this at the system level and try to do something for the program. But most OSs take, I'm not saying this is too expensive to run at the OS level, let the application programmer deal with it and basically throw the ball back in the user's, the application programmer's code. Okay. So I'm going to end this lecture here. We'll do deadlock, the other part of the deadlock prevention next time. Okay, this is going to be Friday's class. No class on Thursday as we just discussed.